So in the previous video, we took a look at the Doppler effect and at sonic booms or shock waves. And with the shock waves, I mentioned that wave fronts would be piling up and adding together. This is an example of a phenomenon called superposition. Now, we'll start here by recapping a little more what superposition is. We've run into it before in context of things like forces, where, for instance, if we said that two objects are interacting with a third object, we could pretend that first one object and then the other object is acting with it, calculate the forces, then add the forces together as a vector to get the net result. As applied to waves, and here I'm going to mostly be thinking about transverse waves, and in the next video series we'll look at sound waves. The way this winds up working out is, let's say I have two pulses that are going down a string, say like this. As they move along, what we can basically do is say that what the shape of the string looks like is what you would have if there was only one pulse on the string and then the other, and then add the two results together. So for instance, when these two pulses meet, what we'll have is one pulse that's double the height. So here would be the one wave here, and then just on top of it, at every x coordinate, I would be adding the other wave on top to get a resultant that looked like a wave twice as high. Then they would continue to just pass right on through each other, so eventually you would see two pulses. You would eventually see two pulses drifting back apart on the way out. Now, when we actually start adding two waves, they could either reinforce each other like you have here, or they can work against each other. We call these constructive and destructive interference, and it is possible to have states that are sort of in between pure constructive and pure destructive. But let's go and take a look at constructive interference here for just a second. So let's say you have your stereo speaker wired up correctly, and you are sitting right in the middle, in the line that bisects the two speakers of your stereo. You're of course listening to your favorite collection of tuning fork recordings. And so what would happen if the speakers are wired up correctly is that since the sound travels the same distance from both, crest will meet crest and trough will meet trough at that point. So coming from the one speaker, you would see a waveform. Let's say it looked something like that. And then coming from the other speaker, you would see, well, I'm just going to be lazy and say you'll see exactly the same thing. There we go. And so when you add them up, what you'll do is at every single point, you will take the values of each of these at that point and combine them together. So here, this plus this is 0 here, 0 there. You get 0 here. And let's say here, let's look at this crest here. This crest here, These are two max values that when I add them together, I'll get this much and then that much again. In between, this is like halfway up here, ditto there. So you get, something looks like that, and so forth. So here, the two would add up to be a full minimum. I'll just put in a few more dots. So what you would get is basically the same wave, except the amplitude would be double. So that's why when you're sitting right between the speakers, the sound sounds the loudest. Now, sometimes if you wire up a stereo, if you accidentally wire it incorrectly, you might notice that the sound sounds muddy. I'll get into that more in a second, but first we'll just start by thinking about your noise canceling headphones. So this is an example of destructive interference. So again, you'll come in, you'll have, so there's your signal. Now what your noise canceling headphones will do is if you say aren't listening to any music and you just have them turned on, there's a microphone listening to the sound in the outside, and it will generate a signal that is the exact upside down of the sound from the outside. So when you add those together, you get nothing. Now usually you're listening to something, so what the noise canceling headphones will do is add the upside down of the sound wave that's coming from the outside to the music, so that when the sound coming in from the outside plus the upside down part cancel, you're just left with the music. The reason your noise canceling headphones don't work perfectly, by the way, is more an intentional point of design. Imagine if you're in some public space and somebody was yelling at the top of their lungs that some emergency was happening, and you had noise canceling headphones that worked perfectly. You wouldn't know that you needed to do something about that. So getting back to why the sound from a stereo can sound muddy if you've got your speakers wired backwards. So in most stereo systems, the terminals in the speaker, both on the back of the amplifier and on the back of the speaker, are color-coded red and black. And they tell you very carefully to use a red wire to attach the red terminals to each other and a black wire to attach the black terminals to each other. Well, first off, the color of the wire doesn't matter at all. That's insulating material. That's just keeping the two wires from shorting each other. It could be literally any color at all. But the reason that they go to this elaborate color coding is that if, say, one speaker were wired red to red between the amp and the speaker, and the other one were wired red to black, then that would mean when one speaker flexes out, because the electricity would be going backwards through the other speaker, that one would be flexing in, and you would have the result of the two speakers flexing in opposite directions. You would have basically created your very own noise canceling headset. And so if you sit in the middle, it's going to sound very quiet. Cancellations won't be perfect because your ears can't be placed in the exact dead center, or at least not both of them at once. So the sound will just sound muddy. And this also, a lot of stereos now even have systems designed to suss out that that's exactly what's happening and flip the polarity behind your back so that you don't have to rewire it later. Alrighty. So with that bit of intro, I want to get into thinking about how a wave could reflect. So this is actually something you can kind of try yourself. Just take a piece of string or whatever and tie it to something convenient, the back of a chair, something like that. If you snap a wave down the string, like so, just a pulse, and the end is tied down, when you watch the pulse come in, when it reflects back off the boundary, you are going to see it reflect back upside down of the way it came in. So we'll call this a fixed boundary here. And we can think about this a bit intuitively, because as the pulse is coming in, if we look at the wall here, as the string comes in on the wall, there's going to be a force of the string on the wall trying to pull the wall up, because the string is up here, there's tension, the string is trying to pull the wall up. By Newton's third law, that means the wall would have to exert a downward force on the string. And so that would be the same difference as if you snapped the string down. So effectively you make a new pulse heading out the from the way it came in, but upside down. So that's if you have a fixed boundary. The other extreme position, and it is possible to have things that are sort of in between these, but we won't worry about that in this treatment. So the other possibility is if you have a free boundary. Now here, the string is free to float up and down. About the best you can do with this, and it's a little fussy to do, is if you use something like a jump rope, piece of rope, something like that, hold it in your hand and let it dangle vertically and snap a pulse down. You can see that as the pulse comes in, since it's free to move here, what will happen is it will reflect back right side up. So that's if you have a free boundary. This turns out to be an application of something called Huygens Principle, which is usually more reserved for optics. But now, just as a thought experiment here, let's say you have a string that's attached on both ends. So let's make it a fixed boundary. So if you send a pulse down, like so, it'll come out and reflect back upside down. Now if you keep sending pulses down, eventually these pulses coming back will interfere with the pulses that are being sent down. And in most situations, what will wind up happening is these pulses will generally start canceling each other out. And so you won't, you'll see the string or whatever move around a little bit, but not a whole lot, unless you happen to get them moving at exactly the right frequencies, which you'll get to see in the school video I'm dropping in right here. So here I have a string attached to two fixed ends. On one of the ends is a little motor that is shaking the string up and down. Right now you'll notice that we're fitting half of a wave in. Now I'm increasing the frequency. In fact, it'll be double. And you can see that we fit an entire wave in. There's always going to be a node on the left because that's a fixed end, and a node on the right because that's a fixed end, but we've now picked up a node in the middle. Notice also that there are antinodes between the nodes. We have 2 loops, 1 entire wave. So now we're going up to the third harmonic. And again, it's the same deal. We can pack 3 loops in to have nodes on each side. Now notice here as I change the frequency up to the 4th harmonic, as we pass through, you'll notice that the amplitude pretty much dies down until I hit the 4th harmonic. This is because if we're oscillating at any frequency other than a resonant one of the standing wave frequencies, the waves that are being sent down the string from the motor to the opposite end will more or less destructively interfere with the ones coming back, at least when averaged out over many reflections back and forth. But for these particular special frequencies, the reflections of the waves constructively interfere with the waves being sent down. So now here I'm taking it up to the 5th harmonic. You can see I fit in 5 loops, or 2.5 waves. And you can notice here from how the fluorescent lights are grabbing this, you can actually see that when one is waving up, the other is waving down. So now we're on the 6th harmonic, so we've packed in 6 loops, or 3 complete waves. Now we're on to the 7th harmonic. So 7 loops, or 3.5 complete waves. The 8th harmonic. So 8 loops, or 4 complete waves. And again, the strobe effect from the fluorescent lights pretty clearly shows that in adjacent loops, when one string is going up, the other one it's heading down. So now we're on to the 9th harmonic. So 9 loops, or 4.5 complete waves. And the 10th harmonic. So 10 loops, or 5 complete waves. Okay, so the phenomenon you just saw is something called a standing wave. And we can, so what you saw was that in this particular case, the ends were fixed. And that was because the string was clamped down at both ends. And then there might have been some other spots in between that didn't particularly move. Any point where the string doesn't move with time we call a node. And then you also saw spots where the string maximally moved up and down. Those points get called antinodes. So here's a snapshot graph at t equals 0. So a quarter period of oscillation later, the whole thing is just plain flat. And then at half a period later, it's the upside down of what you had. And then at 3/4 of a period, it's flat again. Then finally, after one period, you're back where you started. So what's happening is the machine was sending waves down. They were hitting the other end and reflecting back, but the phases were just perfect so that whenever a wave met its reflection, it always interfered constructively, creating this what's called a standing wave pattern. Now, what's really happening is you have waves moving both right and left that are interfering to give this pattern. So just so we've got everything dimensioned out here, this entire distance here is one wavelength. And so this distance here, which is half a wavelength, sometimes gets called a loop, and that's something that I tend to go with too. And this funky symbol there, that is a lowercase Greek lambda. You draw one like that. So let's see if we can figure out what the possible frequencies and wavelengths we could conceivably have for these. So let's start with the example you saw in the video where both ends are fixed. There we go. So let's say the distance between the two ends is L. Since we're fixed on each end, we are constrained to have a node, because literally the string can't move there, so it's got to be a node. The fancy term for this is we say that this is a boundary condition. And we're just saying, because it's fixed, this has to be a node right here. All right, so now let's think, what is the longest wavelength I could possibly fit? Well, it would be if I go from just one node to the other like that, so we'll call this case 1. This would be what we call the first harmonic, or the fundamental. And if you take a look at this, this is just one loop, which is half a wave. So I can fit a half a wave into between the two ends. So the wavelength of the fundamental will be 2/1 times L. And yes, I know I could just write 2L, but bear with me here for a moment. All right. what's the next short? I can't fit anything longer because I just started a node and I wouldn't have another node. So I'd have to go something with the shorter wavelength. What's the next possibility? Well, the next possibility would be if I could sit in two loops like so. So this would be a node right here. So this is one loop, that's another loop. So this would be the second harmonic. And again, if we look here, we can see that I can fit an entire wave in if it's the second harmonic, right? Because there's two loops there. So we can write, say I fit two loops in, so a loop is half a wavelength, so this is 2/2 of this new shorter wavelength, lambda 2, or we can say that the wavelength is 2/2 times the length. Yeah, I know, it's just the length, but bear with me. All right, what's the next one we can do? Well, we still need to have a node here. So the next possibility would be if I cram 3 loops in. So this would be choice 3. So this would be a node right here. That would be a node right there in addition to that. So 1, 2, 3 loops. So this would be my third harmonic. So within L, I say we'll fit in 3 loops. A loop is half a wavelength. And again, this is of a shorter wavelength here, lambda 3. So we can get that the wavelength of the third harmonic will be 2/3 times L. All right, so I think we can start to see what a pattern would be for us to figure out what the wavelength of the M of just some arbitrary harmonic it would be. The things that never change are the 2 and the L. And if it's the first harmonic, we had a 1 here. If it's the second harmonic, we had a 2 here. If it's the third harmonic, we had a 3 here, and so forth. So right, this is 2/m times L. Now, m here is not a mass. This is just literally just an integer. 1, 2, 3, whatever. So the idea is if you want the first harmonic, you'll put a 1 here, you'll put a 1 here. That's the wavelength of the first harmonic. If you want to set the 17th harmonic, you put a 17 here, so lambda 17. You put in a 17 there. That would be 2/17 L would be the wavelength of the 17th harmonic, and so forth. We can also get the frequency, because the speed of any wave is equal to frequency times the wavelength, so we can rewrite that as the frequency is equal to speed over the wavelength. So putting in, we get the frequency of the mth harmonic will be m times the speed of the wave over 2L. And again, m could be any possible integer, 1, 2, 3, and so forth. So the frequency of the fundamental is just going to be this V over 2L right here, because remember, for the fundamental, m would just be 1. So we could also write this as Fm equals m times the frequency of the fundamental. And that's what you saw in the demo video there. If you go back and take another look, you can see that the frequency of the wave, which is showing on the digital display in the lower right-hand corner, kept going up in even steps. Okay. What's the next possibility we can look at? The next possibility we can look at is if both ends are free. This is really hard to do with a string or something like that. About the closest thing I can think of here for a transverse wave is if you have a somewhat floppy rod, like maybe one of those really cheap plastic rulers, something like that. And you can grab it and you can start shaking it, grab it in the middle and start shaking it, and you'll see the outside ends flop around. This is because we're going to need to have, if it's free, we're going to need to have an antinode on each end. Otherwise, you won't be able to reflect back perfectly right side up. So let's go through the same exercise and think about what waves you could possibly pack in that would have an antinode on each end. The longest one I can think of would be just like that, where you would have the node in the middle, like so. Well, this is half a loop over here, and that's half a loop over there, so the whole thing's one loop. The next possibility I can think of be antinode, 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 like that. That'll work. So then the nodes would be here and here. So that's half a loop there to make a loop, plus half a loop there, 2 loops, or a whole wave. And then finally, let's go and fit in another one. This would be the third case I can think of. I would have a nodes here, here, and there, something like that. So half a loop here, half a loop there makes a loop. Got a loop there and a loop there. That's 3 loops. So it turns out it's exactly the same deal. I can fit 1 loop, 2 loops, or 3 loops in between. And so I get the exact same results as if it were fixed. Now, while this is kind of tricky to do with a transverse wave, you do get this sort of thing all the time in sound waves. For instance, if you have wind blowing across a pipe that's open on both ends, that would correspond to a free situation. But more on that in the next video series. Finally, let's go take a look at a fixed free case, because that's all that's left. So over here, this end's fixed, so I'm going to need a node over here. Then over here, the string will be free to flop around. I'm going to need an antinode over here. Now let's start to think about what we can pack in. So here, the longest wavelength I can possibly think to pack in is going to actually be a quarter of a wavelength, half a loop. Just go straight from node to antinode, nothing in between. That would be half of a loop. So my first harmonic, or fundamental, the entire length of this, I could fit in half of a loop or a quarter of a wave. So the wavelength of the fundamental here is 4 times the length between the ends here. All right, well, let's think about the second harmonic. So for the second harmonic, if I were to stick in a loop in between, so there's a loop, so there's another node right there, this would go node, antinode, node, antinode. Okay, that works. That's the next longest possibility I could possibly pack in. And what I've got is here's a loop and a half, or 3/4 of a wave. So the wavelength would be 4/3L. Let's do one more just to see if we got the hang of it. The next thing I could imagine doing is sticking in still yet one more loop, something like that. So that would be 3. So there's a wave and another 1/4 of a wave. So I was stuck 5/4 of a wave between the ends. So that means that the wavelength would be 4/5 of the distance between the two ends. Now, to write down our relation for the wavelengths, we can see the pattern. For the first harmonic, this is 4 over the first odd number. For the second harmonic, it's 4 over the second odd number. For the third harmonic, it's 4 over the third odd number, which is 5, and so forth. So the way pretty much every book written since about 2000 will express this. And I'll give you another way if you don't like this one. So I'll write it like this. But then what they expect you to know is that here, these numbers are going to run 1, 2, 3, 1, 2, 3, etc. This will be the number of the harmonic. And then this will run 1, 3, 5, and so forth. These will be the odd numbers. So the idea here is, let's say you want the 7th harmonic. Okay, you go put in a 7 for the M here, and then that would be 4 over, let's say, so we need what would be the 7th odd number. So let's start counting them off. 1, 3, 5, 7, 9. Okay, we're up to the 5th odd number. 11, 13. So this would be lucky number 13 down there. I know that there's been a lot of work done in trying to figure out what would be the most memorable way to present that, so I'm not going to fight it. And probably most of you will be happy with that. But if you want to still stick with the idea of plugging in the same number m every time, there is another way you can write this. You can write this as lambda m equals 4 over 2m minus 1l. 2m minus 1 is literally just the equation for the mth odd number. So again here, if I were to put in, say, m equals 1, this would be 2 times 1 minus 1 is 1. If I put in 2, 2 times 2 is 4, minus 1 is 3, which is the second odd number. Or if I wanted to, say, find the 7th harmonic, so we 4 over 2 times 7 minus 1L. 2 times 7 is 14 minus 1 gives me my lucky 13. So whichever way you want to do it, roll with it. Like I say, I'm going to assume that since basically every book out there now writes it this way, that's the way that most people find accessible. All right, so we can also come up with the corresponding relationship for the frequencies. So remember, V equals F lambda, so that will give me that F is equal to V over lambda. So plugging in, if I do it in the style of on the left, that will give me Fm equals m times v over 4L. And again, here, this m here is going to be 1, 2, 3, and so forth, while this one will be the corresponding odd number, 1, 3, 5, 7, and so forth. And again, this bit right here will be the fundamental. So if you prefer, you could write Fm is equal to m times the fundamental, but again, this is going to be 1, 2, 3, and then this is the corresponding odd numbers, 1, 3, 5, and so forth. Or, if you want to write it the old school way, you would write that the mth harmonic is 2m minus 1 times v over 4L, and that bit right there will be our fundamental. And then we just plain use m equals 1, 2, and 3, and so forth on both sides of the equation, just like we did up here. So again, whichever you find more convenient. So here then we would be writing that the mth harmonic is equal to 2m minus 1 times the fundamental. Again, 2m minus 1 is just the math equation for the mth odd number. Alrighty, in the next series of videos, we will be taking a look at this with sound waves. Catch you on the flip side.